So again, as Frank said, I'll be talking today about the missing galaxies in the nearby universe. This is something known as the missing satellite problem that astronomers have been studying for decades. And one way to attack this problem is by looking at the oldest stars in the nearby universe. So this is work I'm doing with the Hubble Space Telescope. It's a program I put together a few years ago. It was about 113 orbits on Hubble, and the team of folks I show here from around the world worked on it with me. I've listed their names. I won't go through them all, but some of them are observers on Hubble, like myself. There's some folks here who had time on the Keck telescope in Hawaii, and then there are also some theorists on this program who study both the evolution of galaxies in time, the evolution of the universe, and the evolution of stars. So it's a good mix of people who use telescopes on the ground in space, and then also theorists. So this is a simulation from Ben Moore at University of Zurich of how the structure of the universe evolves with time on the right-hand side here. So this little number counting down here is redshift, for those of you familiar with it. So this is redshift going into the present. And the beginning of the simulation, I'll back up here when it stops so you can see it again. The beginning of the simulation starts right after the Big Bang. And then the matter in the universe coalesces in this filamentary structure you see here. This is how theorists predict the universe evolved under the paradigm of cold dark matter. And the assumption here is that there's dark matter permeating the universe. It's cold and dark. That's why it's called cold dark matter theory. And you can't see it, but what you do see are the galaxies that form in the filaments along the structure of cold dark matter. So dark matter is the scaffolding upon which galaxies are built. So the dark matter permeates the universe, and then these filaments are where you have large galaxies. So these bright red points here are galaxies like the Milky Way, giant spiral galaxies or giant elliptical galaxies, and then the little tiny dots are satellite galaxies. The cold dark matter theory conforms with a lot of the observable phenomena in the universe, but one thing it strikes out on is it overpredicts the number of tiny little galaxies. So that's a long-standing problem with the cold dark matter theory. So here's a zoom in of an environment like our own Milky Way. This is from my collaborator Jason Tumlinson, who also works here at the Institute. He's a theorist and an observer. And the simulation I'm showing here is about 1 million light years on a side. And so this is the environment around a galaxy like our own Milky Way. And this shows in his simulation here, in Jason's simulation, the expectations for the distribution of dark matter in the nearby universe, the very nearby universe, within 1 million light years. And it might not sound that nearby, but this is roughly the sphere of influence of the Milky Way. So the Milky Way would be sitting here at the center, and we know there's a galaxy there, it's the Milky Way. And then there's all these little clumps of dark matter orbiting the gravitational well of the Milky Way. And there are hundreds of them in this simulation. And when you look at the number of galaxies actually orbiting the Milky Way, there's only a few dozen. So it's off by a large amount. It's grossly off, the number of observed satellite galaxies compared to the predictions of the cold dark matter theory. So this is the missing satellite problem, that cold dark matter says there's lots of little clumps of dark matter out here, and yet we only see a few dozen galaxies. And these clumps of dark matter are the seeds of galaxy formation. So this was a big shock when people started doing censuses of galaxies, comparing them to theory. So things are off by more than an order of magnitude. So that's it. In summary, theory predicts more dark matter clumps orbiting the Milky Way than the number of dwarf satellites we actually see. That's the missing satellite problem. So a solution to this was proposed a while back, and it has to do with the reionization of the universe. So this is a cartoon I'm showing here with the Big Bang on the left and the modern era on the right. And time is just progressing from left to right here in this cartoon. And this is the evolution of the universe. So the Big Bang is right here. Right after the Big Bang, there's a short period here called the Dark Ages, where the universe cooled enough to become neutral. So you have hydrogen is neutral. You just have electron orbiting the proton. Things have cooled down, and the stars have not yet come on. And then the first stars and galaxies are born right here, shortly after the Big Bang. And ironically, what happens is when the first stars and galaxies come on, they illuminate everything. That actually snuffs out a lot of star formation all around the universe, because that light comes on. It's a very strong source, ultraviolet light, and it blows out the gas out of a lot of little dark matter clumps and turns off the star formation. That's the theory here. So you have the first stars and galaxies come on. They come on so rapidly, they actually shut off the star formation in a lot of parts of the universe. So this is the era of reionization, when the universe gets ionized from those first stars and galaxies forming. Then after that era is done, galaxies continue to evolve. New stars are born from enriched gas. You've heard this before. We're all made from star stuff. So stars explode. Their material goes out into the interstellar medium. New stars are born from that enriched gas. And time goes on. And here's when the sun would be born at this point in history. And here we are today. So the sun was born about 4.5 billion years ago. Here we are sitting here in the modern universe, and we look back in time. So now we return to Jason's simulation. So this is the dark matter distribution around a galaxy like our Milky Way. And the theory goes He's highlighted here in green. Those are the satellite galaxies that formed lots of stars, and that's why we know about them. So for decades, we've known about these satellite dwarf galaxies. These clumps of dark matter were large enough to accumulate a bunch of gas, have stars form, and then they continued forming stars until the present era. So these little clumps here all continued forming stars to the present day. And this is what we knew about galaxies up until the stuff I'll show you tonight. This is the assumption that's been made about all galaxies, that galaxies are groups of stars built upon dark matter that have a wide range of ages. They have stars born in the early universe, and they have stars continuing to form up until today. I mean, Frank just showed this press release with these galaxies formed stars very recently. So until recently, every single galaxy had not only old stars, but younger stars as well. What's that? Okay, I thought maybe it was me, sorry. I thought I turned off my phone, I was just checking. Okay, so anyway, this is the theoretical prediction for the kinds of galaxies we've known about forever, for decades, orbiting the Milky Way. The problem is here, you see that a lot of these little clumps of dark matter aren't highlighted. They just stay dark. So this is what the theory predicts, that most of these dark matter clumps never form stars, and that's why you don't know they're there. But they are there. It's just clumps of dark matter orbiting the Milky Way. If this is true, here are these red ones I've highlighted. There should be fossil galaxies out there that we didn't know about that are just ancient and are made from pristine gas in the early universe, form stars, and then were shut off by the reionization of the universe. So these ones are on the cusp. You have the galaxies that kept forming stars because they were big. Then you have these smaller guys that started to form stars in the early universe, and then the lights came on, and they snuffed them out, and they never formed stars again. So these are ones that kind of like a transition between the galaxies that kept forming stars and the ones that never formed stars at all. And then here I'm highlighting both. So in green now, these are the galaxies that continue to form stars. These are the classical satellites we've known about for decades. In red and pink here, these are the galaxies that got snuffed out right after the Big Bang. And then most of these little clumps never form stars at all. And that's the possible theoretical solution to the missing satellite problem, is that these dark matter clumps are just sitting out there orbiting around. They didn't form enough stars for us to see them. So if this is true, we need to find these fossil galaxies, these ones in red. We've known about these ones in green for a long time, and Frank showed some of those tonight. I'll show you some pictures of other ones. The key here, since we can't see the dark matter clumps without stars, to prove this theory, you got to look at these pink ones and find evidence for fossil galaxies. So that was the goal of the Hubble program we decided to undertake. So if this theory is true, we should have ancient dwarf galaxies besides the bright galaxy we've known about for decades. This is Fornax, one of the brightest satellite galaxies of the Milky Way. It's a group of stars, millions of stars with a very wide range of ages, and a wide range of chemistry. So when I talk about chemistry, I'm always talking about relative to the sun. So there's some stars that have just as many chemical abundances as the sun, and we have some stars that are much, much more metal poor than the sun. They have like 1% of the metals the sun has. So wide range in chemistry, wide range in ages, from right after the Big Bang, 13 billion years old, to up to just a few hundred million years old. So this is Fornax, has a wide range of ages. So a big step forward in the missing satellite problem was the Sloan Digital Sky Survey. This was a survey of a wide range of the sky done with a small telescope on the ground in New Mexico. It's done from the ground. This patch of sky is a summation of all the data from the Digital Sky Survey, from a paper from Belakurov et al. In 2007. This is tens of degrees across in the sky, and he basically summed up all the data from this scan of the sky. And this scan revealed a lot of structure in the nearby universe that we didn't know about before. And your eye is already probably picking up on some of it, but I'll highlight it here. So in white, I've highlighted 3 streams of tidal debris. So this is the Sagittarius stream along here. This is the Orphan stream over here, and this is the Monoceros ring. These are debris streams from satellite galaxies that fell into the gravitational well of the Milky Way and then got disrupted by the tidal forces. So the galaxy is not really there anymore. It's getting eaten alive by the Milky Way's gravitational well, and it's just strewn across the sky, this stream of stars here. Then they also found a lot of other little satellite galaxies, which I've highlighted here in pink. So these are new galaxies that were too faint to be noticed before, but they're little overdensities of stars. So this went part of the way towards solving the missing satellite problem. So we had a few dozen galaxies, and this found that, well, okay, some of them are being disrupted, which is making them hard to see, these big streams. And then other little ones were too faint to see. These little faint ones are excellent candidates for these fossil galaxies that the theorists predicted. They said, okay, well, we didn't know about these ones before. Maybe these are these ancient fossil galaxies, and there should be a big support for this theory. So these are the ones we decided to target with Hubble. Before I go on to that, this is the Dark Energy Survey. This came out with some results last year. It found 9 new satellite galaxies. This is a projection on the sky of where they found them, highlighted in blue here. Here's where they are in a different projection from 2 different papers that came out last year. So there are a lot of surveys right now from the ground. This is a really active subfield of astronomy where people are banging away, mapping the whole sky, trying to find the missing satellites. But they're not coming up to the hundreds of satellites that theory predicts. They're increasing the number from a few dozen to several more dozen, but they're not coming up to the hundreds, and that's because most of those galaxies are probably dark. They have no stars. They're just clumps of dark matter. But we are finding more and more satellites. So just to put things in perspective, just to give you a sense of scale here, here's a giant spiral galaxy of about 100 billion stars in the upper left. This is like the Milky Way or an Andromeda. And down here is New York City. I'm from New York, so this is the comparison I'm going to use. So this is 10 million people, okay, in the city of New York. Typical galaxies that orbit the Milky Way that we've known about for decades are like this here, like Fornax, 10 million stars. You scale down New York City, you're talking about one theater showing The Lion King in New York City. So this is the relative scale here we're talking about. These ultra-faint dwarf galaxies go down even further. So they only have 10,000 stars in them. They're barely a galaxy at all. And now you're talking about one guy in New York, the host of Jimmy Fallon's show. That's how the relative scales here we're talking about. So the giant spiral like Andromeda or the Milky Way, a classical dwarf like Fornax, and these new ultra-faint dwarf galaxies that were only recently discovered. So when you show people, especially astronomers, when I give this talk to professional astronomers in particular, I sometimes get into arguments afterwards where they say, well, why is that even a galaxy if it only has 10,000 stars in it? Because there are star clusters that have many more stars, and that's true. So this is a globular star cluster, like the picture that Frank handed out tonight, like Omega Cen. This one's actually the picture from that Andromeda image I took a while ago. That's a star cluster in Andromeda. It's a globular star cluster of 100,000 stars, and this is an ultra-faint dwarf galaxy with 10,000 stars. So why is this a galaxy? And that's a star cluster. And the reason is because it's dark matter. This is what I was talking about earlier. Globular clusters, as far as we can tell, have little to no dark matter. So if you measure the mass-to-light ratio, which is something astronomers do in these objects, in units of the sun, you get a mass-to-light ratio of about 2, which is consistent with an old population of stars. That means compared to the sun, there's the ratio of mass to light in the sun. These globular clusters have about twice as much mass-to-light ratio. And that's because most of the stars are really faint and dim compared to the sun. Most stars in the universe are really faint and dim compared to the sun. In contrast, these ultra-faint dwarf galaxies have a lot of dark matter, again, because dark matter is the scaffolding upon which galaxies are built. So galaxies have significant dark matter. The classical dwarf galaxies we've known about for decades have mass-to-light ratios exceeding 10. And the ultra-faint dwarf galaxies have mass-to-light ratios exceeding 100. So these new galaxies are almost entirely dark matter. There's just a big clump of dark matter there with a few stars sprinkled on top, which is consistent with this theory that the theorists used to predict the solution to the missing satellite problem is that you had the dark matter there, a few stars formed, and then things were turned off. The lights were turned off when the most of the universe came on with star formation. Another big difference is that globular clusters are usually what we call simple stellar populations. All the stars to first order are just one age and one chemical composition. You have a cloud out there in space, it collapses, and you form a bunch of stars. They all have one age, one chemical composition. Galaxies have a wide range in ages and a wide range of chemical composition. That's true of every galaxy that we've known about until the ones I'll show you tonight. So this is a plot now of, just to put these things into perspective, this is luminosities here relative to the sun. So 10 to the 6 is 1,000,000 times the luminosity of the sun. This is diameter in light years from 1 to 1,000. So star clusters fall over here. These are globular clusters. They have up to 1,000,000 times the luminosity of the sun, or maybe even 1,000 times the luminosity of the sun, but they're pretty compact. They're on the left-hand side of this diagram. The classical dwarf galaxies are shown here in blue, so they're much more extended, and they're generally brighter than star clusters. They're up and to the right. These ultra-faint dwarf galaxies are down here. They're an extension of these dwarf galaxies to fainter luminosities and smaller sizes, but they're not as compact as globular clusters. So they're mostly dark matter, and they're these wispy things with just a few stars in them. And so we decided to look at these 6 very closely with Hubble, because Hubble is excellent in measuring the ages of stars to test these theories. So how do we know if a group of stars is old? Well, there's 2 ways you can go about it. One is to get spectra of these stars. You take the light from the stars, you spread it out into its rainbow, and then you look for features in that spectrum to see what kind of metal abundances there are. And so if we want to see if it's old, it should have a low abundance of metals. If it was born in the early universe before there were many generations of stars, the gas should be pretty pristine, and so there shouldn't be a very high chemical composition in these stars. We also do photometry. We measure the brightnesses and colors of the stars, and when we do that, we can see what masses are left. Only low-mass stars, less massive than the sun, should be present if it's old, because massive stars, more massive than the sun, die very quickly. So these are the 2 tests we do to see if these things are actually old galaxies. So here's a spectrum for an ultra-faint dwarf galaxy. And it tells us a couple different things. So well, it gets broken into its constituent light from blue, green to red, and these little dark patches in there are absorption features from metals in the atmosphere of the star. So by measuring the velocities from the Doppler effect of these absorption features, we can measure the motions of these stars. And the motions of the stars in the ultra-faint dwarf galaxies imply there's a lot of dark matter there. So the matter in these galaxies, the luminous matter, is feeling the presence of the gravity from the dark matter. The absorption features, these little patches here, are also very weak. So it means these stars have 100 to 10,000 times fewer metals than the sun. So these stars were really born in the early universe when the gas was still pretty pristine. And this is also a little cottage industry in astronomy. A lot of people are looking for the first stars and the earliest stars and the oldest stars. And folks who are looking for the most metal-poor stars have found a lot of them in these ultra-faint dwarf galaxies. So this is fertile ground for these searches. So this is the same handout you have tonight, this Omega Sen. So it's fortunate that Frank handed this out. I'm going to sort, this is an image from Hubble with the Wide Field Camera 3. This is a camera I worked on before I switched over to James Webb for a while. I'm going to sort this. This is from my colleague, Jay Anderson. I'm going to sort this in color first, from left to right. So hotter stars that are blue will be on the left. Cooler stars that are red will be on the right. Then we're going to sort it in luminosity with brighter stars at the top, fainter stars at the bottom. When you do that, you see that stars don't just have random colors and random brightnesses. They actually trace out a very specific pattern. My wife calls this the duck diagram because her mind's over duck. But anyway, here's the body, here's the neck, here's the beak. But main sequence stars like the sun that are burning hydrogen fall down here. And then after they exhaust their hydrogen, they go up here and become red giant stars. And then they finally burn helium and they become this thing called horizontal branch stars because this distribution is horizontal. So they burn helium and then they die as white dwarfs. So when you sort a population of stars by brightness and color, they're not random. They trace out a very specific pattern. That's the life cycle of a star. And that's how we can use that information to tell how old a group of stars is. So that's where those stars now fall in that image of Omega Sen, which is on the handout over here. So here's measurements of a galaxy. This is brightness again on the y-axis here in these funny units astronomers use. So this is in a filter 814, so 800 nanometer filter. The 606 minus 814, 600 nanometer minus 800 nanometer filter. So this is a color with redder stars on the right, bluer stars on the left, brighter stars at the top, fainter stars at the bottom. Hydrogen burning stars fall along here. Here's this kink, and then they exhaust hydrogen in the core, and then you become a red giant star. And that's how you measure the age of a population. So these are low mass hydrogen burning stars, more massive hydrogen burning stars, and then they peel off and become red giants. So these are stars that are still burning hydrogen in the core, and these are stars that have exhausted hydrogen in the core and become giants. So that's the clock. That little kink right there tells you that's the best clock in astronomy right now. There's a lot of different ways to measure the ages of stars, but that's the gold standard since Alan Sandage started doing this in the 50s. So this is what you get for a population that's 13 billion years old, an ancient population. And that's what it would look like for a population that's 6 billion years old. And that's what it is for 13 billion years old. It's a very dramatic difference. And the reason why is because the massive stars die more quickly than the less massive stars. Ironically, if you're a massive star, you have a lot of fuel, but you're very bright and you burn it very quickly. So you leave the main sequence and you become a giant more rapidly than these stars down here. So here's the Carina classical dwarf galaxy. This is out in the local group. Again, a pretty massive dwarf galaxy we've known about for decades. And here's its color magnitude diagram. So this is brightness on the y-axis, color on the x-axis. And you get these three distinct little shapes here. Each of those is from a burst of star formation. If I put models on top of that, this is where stars about 500 million years old would lie in this brighter curve here. Stars 5 billion years old would lie along this intermediate curve here. And really old stars, 11 billion years old, would lie here. So this is a kind of curious galaxy. You don't usually see these episodes of star formation, but in this one you did, and it makes it kind of interesting to show the clock in three different places, 1, 2, 3. And this is similar to the stories we've seen for a lot of dwarf galaxies. There's a wide range of ages. You don't see just old stars, you don't just see young stars, you usually see a wide range of ages. So here's the ones we decided to look at again tonight, the ultra-faint dwarfs, and again I looked at these with Hubble. They're kind of a sample of about 6 galaxies out of the recently discovered ones from Sloan. And this is what it looks like when Hubble looks at one of these. So in the background here, I'm showing a digital sky survey image. And then Hubble has a pretty small field of view compared to some of these ground telescopes. So the footprint from Hubble, from its advanced camera for surveys, is one of these blue tiles here. We kind of went and tiled that part of the galaxy. We turned on Wide Field Camera 3 in pink here in parallel. It kind of missed the galaxy here, so it was just getting a sample of some of the stars in the background. This is about 200 arc seconds on a side. This is Leo 4. So this galaxy is further out from the Milky Way, so it's a little more compact in the sky. So if you look carefully, you can see there's an overdensity of stars right here compared to the background. And so we stuck ACS, the advanced camera for surveys, right here. We stuck Wide Field Camera 3 out here. We got pretty much nothing. But this one measured the galaxy. And so that's the image we got of Leo 4 in that patch. That's this patch of sky right here. This is the Hubble image. It's about 16 orbits. We hand out time on Hubble in units of orbits. Hubble goes around the Earth every 96 minutes. That's the currency on Hubble. So people ask for 5 orbits, 10 orbits, 100 orbits. This was 16 orbits on this one galaxy. We looked at 6 galaxies in total. It's a fairly deep image. Like a lot of images with Hubble, when you're trying to go deep, you get the rest of the universe in the background. So there's all these really pretty galaxies in the background. And a lot of people like those because the stars are just points that are kind of boring. But for me, it's wasted real estate because every one of these patches is where I can't make measurements of the stars. So people like these galaxies. They're just kind of irritating to me. But I'll zoom in on a patch here. So here's this yellow box that I'm going to zoom in. So again, you have these nice, beautiful galaxies in the background, which I just mask out and throw away. And then you have these points, which are stars in Leo 4. And I'm going to highlight 2 of them. These are the most massive hydrogen-burning stars in Leo 4. So these tell you the clock. So when you get measurements of the brightnesses and colors of these stars, that tells you how old the galaxy is. So these are the brightest hydrogen-burning stars in Leo 4. So here's the image again. And what I'm going to do now is highlight the stars in this image and show you how they tell us the clock for the galaxy. So these are the stars in Leo 4. And if I sort them in color and luminosity, that's where they fall at an age of around 13 billion years. And now I can use theory of stellar evolution to roll back the clock here. So now I'm taking the data and just morphing it backwards in time towards the Big Bang. So now this is what the data would look like if we made that measurement a billion years after the galaxy was born. So there's brightness over here, color over here. And now the clock's rolling forwards to the present era. So 5 billion years, 6 billion years, and here's the clock is right here, this kink. This tells you how old the population of stars is. Until you get to the galaxy being about 13 billion years old today, and those are the points, and this is where they fall in that image. So these are the data we got. So we got 6 of these duck diagrams. Like I said, these color magnetic diagrams, and my wife calls them duck diagrams. And the first one we got was here. And now here's full disclosure. I'm an observer. I have a team of folks on here. Some work on Hubble, like me. Some work on Keck. I have some theorists on the team. And I'm used to theorists, not to be disparaging of theorists, coming up with a theory, and then you go test, and you go, well, let me revise that theory. So we got these data right here, and because I work on these kind of diagrams a lot, I immediately saw in my office that this was a very ancient population, which is not what I was expecting. I wrote this proposal to measure how old these stars were, and I was sure, just like every galaxy we've ever measured before, there would be young stars and old stars. But instead, the stars were all just old. And I almost fell out of my chair. And you're looking at these and going, okay, it's a bunch of yellow dots. But for me, it was really surprising because I did not expect the theory to be true. And so I called up Jason Tumlinson, who made that simulation in the beginning of my talk, dragged him down to my office. He works 1 floor up from me here in this building. And he said, well, yeah, that's what it's supposed to do. They're supposed to be old. And I said, yeah, but I didn't think that was really going to happen. I thought there was going to be young stars and old stars, just like every galaxy we've ever looked at before. So those were the first data that executed in the program, Hercules, satellite of the Milky Way. And then we got the other 5 galaxies. And they're all in different positions in each of these diagrams here because some are closer, some are further, so it makes the stars brighter and fainter. But if you do this kind of work, you look at each of these and you say, oh my God, the stars are really ancient in every one of these galaxies. And they also look very similar. These diagrams all look very similar to each other. So just for a comparison, without using any theory, I'm going to take data from another well-studied object that we use to make comparisons to data like I just showed you. This is M92, NGC 6341. It's one of the most well-studied ancient objects in the universe. It's a metal poor star cluster. Alan Sandage looked at this in the 1950s to figure out how stars evolve. It's an ancient star cluster. Its chemical abundances are such that the metals in the atmosphere are less than 1% of the abundance in the sun. It's a globular cluster. This is a half-second exposure on Hubble. Now, Alan Sandage would spend nights on the telescope in the ground looking at this with Hubble. So powerful, this is just a half-second exposure. This is the advanced camera for surveys. It's kind of like the CCD chip on here is kind of like your chip on your digital camera now. There's a crack down the middle here, splits the chip into 2 halves. So that's why you see this 2 sections here. But it's a 4K by 4K image, a 16 megapixel camera basically on Hubble. And all these are stars in this globular cluster, M92. This is the color magnetic diagram from those data. So this is the luminosity here, bright stars at the top. Here's the color, red stars on the right. And again, stars don't just have random colors and brightnesses. They trace out this very specific pattern. That's the life cycle of a star. Hydrogen-burning stars, they exhaust hydrogen, go up here, become red giants. They come over here and burn helium. And this is the kink right here. It tells you the age. So what I can do is I can just draw a curve through that and say, all right, I'll highlight the helium-burning stars over here, and then I'll draw a curve through this. And now I'll just compare that to the data I got on those galaxies. This is an ancient star cluster, 13 billion years old. It's been studied for 60 years. So here are the data on the new galaxies that we found. And here's where the M92 data fall when you superimpose them at the same distance. It goes right through the data in every case. And really, this was, I don't know how shocking it is to you, but I was flabbergasted when we did this, that all these galaxies, which, like I said, galaxies by definition usually have a wide range in age. Every single one of them looks like M92. So not only are they all old, they all look exactly like each other to first order, at least by eye. So this was kind of astonishing, but it's a pretty good support for this theory of what's happening at the missing satellites. We've known about these galaxies for decades that form a wide range of stars or a wide range of ages, but the theory of the missing satellites, why we don't find them is that most of them never form stars at all, and between those two categories, the ones that have been forming stars forever and the ones that never form stars at all, should be this transition group of galaxies that just formed old stars and then were snuffed out in the early universe. And that's what this is telling us. These galaxies formed stars right around the same time M92 was formed, and then were snuffed out when the lights came on. These are pretty boring data, but I'll just show them. These are the Keck data we got. So this is number of stars versus the chemical composition. So for stars here, this is 1% of the cellular composition. This is 0.1%. This is 0.01%. So these are very low metallicities compared to the sun. And this is number of stars in the galaxy compared to what fraction of the solar composition there is. So most of the stars fall between 0.1% and 10% of the solar composition. So the stars are very metal poor. They have very few metals. So they're born from pristine gas in the early universe. So this is, again, supporting evidence that these are pristine ancient galaxies. M92, just for comparison, is right here where the green line is. So M92 is a little less than 1% the composition of the sun. It's also ancient and metal poor. So just for another way to compare these data, these are the data from Hercules. I'm zooming in here now on the clock. So the little kink right here, again, this is brightness versus color. And I'm going to take the data from all the other galaxies and superimpose them on here, just to show how similar they are. So this is Hercules in yellow. That's Leo 4 in green. And if you say, well, I can't really see it that well, it's because they're right on top of each other. That's CVN2 in purple. That's Ursa Major 1 in blue. That's Bootes 1 in red. And that's Colbert in brown. So if you put all these galaxies in the same reference frame, their data fall right on top of each other. These are 6 satellite galaxies of the Milky Way, all at different distances from the Milky Way, all different parts of the sky, and they all look exactly the same to the eye. So that implies some kind of global influence affected all of them. And there's a lot of things going on with galaxies form. Supernova blow off all the gas out of the stars, new generations of stars are born. It's a chaotic process. But something synchronized the star formation in all 6 of these galaxies to a very high degree. And one possible thing that's obvious here after you've heard the pitch in the beginning is that it was a reionization of the universe. That would be a global influence that affected all the galaxies. This is where theory tells us the star should fall if all the stars were between 12 and 13 billion years old. They would fall on this gray curve here, which is a good match to the data. The data spread out a little bit more down here because they're a little noisier as you go faint, but this is where the stars would have been born, right along this curve. So just to show you now a little more quantitatively, this is the zoom in now on the clock for Hercules and the theoretical prediction, a random draw on the theoretical prediction of where the star should fall. So one of these panels is the data, one is the model. I won't make you guess which one is which. But you can see the model and the data look very similar. The green curve is M92 again, just for comparison. So that's Hercules. One's data, one's the model. That's all 6 of the galaxies. So in one panel, I'm showing you the theoretical prediction for how the stars should be scattered around a diagram like this, and the other one's the real data from Hubble. And each panel here, they look very similar, right? The distribution of stars is very similar in each case. And so what it is in each case is the model's on the right and the data are on the left. And the theoretical prediction for where the stars should fall in this diagram matches the data very well. I can show it this way too. The gray shading here is where the theory says the stars should fall, and the yellow points are where the stars do fall. And there's excellent agreement in all 6 galaxies. So this really tells us that these are fossil galaxies. Now, it may not be true that the reionization of the universe is what made them old, but we were testing that theory. We said if there are ancient fossil galaxies, these would be excellent candidates for being fossil galaxies. We looked at them closely with Hubble, and they do seem like they're very pristine in their metallicity, and they're very, very old. They're about 13 billion years old. The average age in each of these fits here, this is 13.3 billion years old, 13.6 billion years old. This is 13.9 billion years old. And I know some of you are going to go, wait a minute, Frank a little while ago was talking about the universe is only 13.8 billion years old. There's about half a billion years of uncertainty in these fits due to the models. So it's consistent with the age of the universe. It's not like we're saying this galaxy is older than the universe, but within the uncertainties, these galaxies were all born right after the Big Bang. This one's 13.1 billion years old, 13.1 billion years old, and 12.7 billion years old on average. So these are the oldest known galaxies, these 6. These are the only galaxies where we've measured ages to this accuracy, and all of them are older than any galaxy we've ever measured before. This is another way of showing the same thing. This is the fraction of stars born in the galaxy versus time on the x-axis. So what happens here, so this is looking back in time to the early universe, 14 billion years ago or so, and star formation starts very quickly. 80% of the stars are formed in the very first billion years, and then it kind of tapers off. And the width here is just the uncertainty in the model. So this would be a narrow curve if our models were better. But so the star formation comes on very suddenly, and then there's a little tail as reionization starts to shut things down in these galaxies. So this is a fit to the data for Hercules. This is what it looks like for all 6 galaxies. They all look very similar. Star formation comes on very rapidly. 80% of the stars are formed right after the Big Bang, and then there's a little tail going on for a few billion years afterwards as the reionization of the universe shuts off the galaxies and their stars. So unfortunately for where we live, or maybe fortunately, maybe it wouldn't be such a great place to live, we live in kind of a cosmological backwater. There's not a lot going on in the local group. So this is a box here showing us part of the local universe, 80 million light years on a side. And the kind of work I'm talking about here, where you can use Hubble to measure ages of stars very, very accurately. There are a lot of ways to measure stellar ages that you could do less accurately, you could do them far away. But for doing really accurate ages, you can only do it relatively nearby. And Hubble can do this kind of work in this yellow sphere right here. So that's where we can do the kind of work I'm talking about right now. And it's not a really interesting patch of the universe where we live, unfortunately. So the symbols here, these paperclip-looking things that I drew here as my lame attempt to make a spiral galaxy, these are giant spiral galaxies. The Milky Way is right here at the center. Andromeda is our only other nearby giant spiral. These big red things are elliptical galaxies, giant elliptical galaxies, and the little brown dots are dwarf galaxies, like I've been talking about tonight. So we live in kind of a boring part of the universe. It's out in the boonies. There's not a lot going on here. It's the Milky Way, Andromeda, and a few dozen dwarf galaxies, and Hubble can measure the ages of these galaxies. The James Webb Space Telescope is launching in 2018. It could do the kind of work I'm talking about tonight in a volume 3 times larger, so it gets a lot more dwarf galaxies. It starts to get to the spiral galaxy. That's not what it was built for, though. It looks in the infrared. It's got a much bigger mirror. It's going to measure the ages of galaxies by looking directly back in time at high redshift. So if you look very far away, you're looking in time. So James Webb is going to look at the most distant galaxies and observe them evolving directly. It's not going to do the kind of stuff I'm talking about tonight primarily, but it will do some of that kind of work, and it could do it a little better than Hubble. Folks are also looking at building much bigger versions of Hubble. So this is an active thing going on right now. There's a lot of folks looking to see what are the next big NASA missions in the next couple decades. And people are talking about building a UV optical telescope like Hubble that would have an 8-meter mirror. So Hubble's got a 2.4-meter mirror. People are looking at an 8-meter mirror. That would get out of our little middle of nowhere patch of the universe. You could start doing this kind of work in spiral galaxies, out in the nearest towns. You can actually pick up an elliptical galaxy and lots of other types of galaxies. There are folks who are really ambitious who are talking about building a 16-meter version of Hubble. And this is really stuff that people are looking at right now. The primary motivation for this is to look for life around other stars. So this is the kind of telescope you need if you want to be able to detect life directly on planets orbiting other stars. And if you're going to build such a telescope, people can use it for other stuff too. And people like me, looking for life around other stars is obviously very exciting. I measure the ages of stars. You could do what I'm talking about tonight in this volume of the universe. And that would be a true census of the local universe. You get lots of giant elliptical galaxies, these red things. You'd get tons of spiral galaxies, many more hundreds of dwarf galaxies. You could really get a census of how the universe has formed its stars in the nearby universe with that kind of telescope. I probably would not get a gigantic fraction of the time. Most of the time it would be looking for life around other stars, but you could get some time doing this type of work. So this is the Hubble Space Telescope in low Earth orbit. So most of the work I've been talking about tonight comes from Hubble, also comes from Keck. I worked previously up until a few months ago on the James Webb Space Telescope for the last 8 years. So I'll just give you a little update on that. This is James Webb. It has, unlike a 2.4-meter mirror, it has a 6.5-meter mirror coated in gold. It's a beryllium mirror. And then just to give you a sense of scale, this is the light shield. This is the sun shield. It's about the size of a tennis court and made of a material similar to like candy wrappers. It's got 5 layers here. It keeps the instruments in the telescope in the shade while it's orbiting out around the sun. We're launching that in October 2018. These are the main science goals of James Webb. So it's going to look at the first galaxies in the universe. So again, it'll be measuring the evolution of galaxies, but in a very different way. It's going to look directly back in time at the most distant galaxies. It's going to watch over that cosmic time how galaxies evolve. Of course, it's looking in the infrared. It can peer through dust and gas to see stars and planets being born. And it's going to be able to look for the origin of life. So these are the main science themes of James Webb. Just for comparison, Hubble is in low Earth orbit. On this scale, you wouldn't even be able to see how far away from Earth it is. It'd be orbiting right there. James Webb's going to go out here to a point we call Lagrange 2. It's 4 times further away than the moon, 1.5 kilometers away. And then just here's a comparison of the telescope sizes. Here is a person, 1.75 meters tall. Here's Hubble's meter, 2.4 meters tall. And here's James Webb, 6.5 meters tall in 18 segments. That's ground testing down at NASA of some of the mirror segments, again, coated in gold. People freak out a little bit when you say the mirrors are made of gold. They go, oh my God, NASA's wasting so much money. The whole mirror has about this much gold on the coating of it, okay? So just for comparison. So it's a very thin layer on the surface. Here are the instruments. So we were testing the instruments individually at different locations around the world up until a few years ago, and then we started integrating them into the Integrated Science Instrument Module. That got tested last year at Goddard. So it's NIRCam, which is a near-infrared camera, MIRI, which is a mid-infrared instrument, also a camera and a spectrograph, NIRSpec, a near-infrared spectrograph, and NIRIS, also a near-infrared camera and spectrograph, specifically designed for exoplanet searches. And here's the test chamber at Goddard, where we were just testing. We wrapped up testing of the instruments this last year in February. This is the chamber that will be used to test the instruments and the mirror together next year in April. This is the same chamber that was used for the Apollo lunar module. I walked around inside this a few years ago before they started cleaning it out and for the testing. I have to say, it's crazy impressive. I mean, those are people standing here. So you walk around inside this scaffolding. It's the same chamber that was used to test the Apollo missions. And it's at Johnson Space Center. We'll be starting testing there next year. And that's what it'll look like. So James Webb will be what we call the cup-up configuration. So the mirror is facing up, and the instruments are sitting here facing down, and we'll do some simulations of the conditions in space to test it before we launch it. So just to summarize, the ultra-faint dwarf galaxies are extremely metal-poor. Some of the most metal-poor stars in the universe that we know about are found in these ultra-faint dwarf galaxies, and their chemical abundances in most of the stars are 1/10% to 1% of those we find in the sun. The ultra-faint dwarf galaxies are ancient. 3/4 of the stars formed their star. 3/4 of the stars were formed more than 13 billion years ago. So these galaxies are truly ancient. There are known, as far as we can tell, intermediate age stars, so nothing really younger than 10 billion years old in these stars, and that's very distinct from pretty much not only the classical dwarf galaxies, every other galaxy that has ever been studied. Most galaxies have young stars and old stars. Star formation appears to be synchronized in these objects. Even though there's 6 different galaxies spread out on the sky, they all have pretty much the same star formation history. It's like a guillotine came along and shut off the star formation in all of these at the same time. And that's what you would expect if they were all snuffed out by the reionization of the universe shortly after the Big Bang. And this is consistent with solutions that have been posed to the missing satellite problem. Most of the missing satellites are there, but they just have few or no stars, so we can't see them. Thanks, and I'll show this video of the JWST deployment in 2 years while I answer questions. Thanks.